the next topic. We're going to look at limits at infinity today. Now, although it says we're starting with limit laws, we're just going to spend only a couple minutes on them. Most of the time we'll be spending on limits at infinity. Remember that we have a lot of different techniques to find the limit of a function. We can look at the graph. If we're not given the graph, then we can plug a into f. If we get an answer, if we get a number, then that's our answer. If we get a non-zero number over 0, then we have infinite left and right-hand limits. We should check both of them and see whether the limit exists. And if we get 0 over 0, as we saw last time, that means it's an indeterminate form, and we have to simplify our expression and then try plugging in a again. Usually the way we simplified was by factoring. Now, going back to step 2, right, plugging a into f, right, very basic. There's actually a lot of stuff going on right there, and I want to take a couple of minutes just to explain where we come up with that idea, why that's allowed, and what's the justification for it. So at the beginning of section 2.3, you find these things called limit laws. And what they say is that if you've got functions f of x and g of x, both of whose limits exist at a, then if you're trying to find the limit as x approaches a of f of x plus g of x, well, really what you're allowed to do is you're allowed to just take the limit of f of x separately and take the limit of g of x separately and then add those limits together, right? Just plug a into f of x, plug a into g of x, right? That's how you can get those limits, right? That's not something that's taken for granted. You have to show that in theory. Mathematicians have shown that. They've rigorously shown it. We won't show it here, but it is a thing. Similarly, it holds for subtraction as well. Get out of there. I mean subtraction, right? Also, if you have a constant c that's inside, you can multiply your limit by that c, right? So instead of worrying about the constant on the inside, just find your limit and then plug in c. The same thing also works for multiplication. It's very nice, right? Just find your limits separately and then multiply them together, right? Plug in a and multiply them. And then it also works for division, although the one thing you need to be careful of is that you're not dividing by 0. So we just need the additional condition that limit as x approaches a of g of x does not equal 0. Those are our 5 limit laws. There are a couple more in the book, but these are the 5 that we're going to talk about right now. So I just want to do one example using limit laws. We won't spend a ton of time on this. You won't be quizzed or on these a ton. You might see one problem on them. But I just want to show you why they're important. They're sort of the building blocks of what we use when we take limits. Every time you plug in a, you're really using a bunch of limit laws, even if you don't realize it. So normally if you had a limit like this, you would just say, oh, okay, well, we're going to just plug in -4. And we evaluate it, and we wind up getting, I think it's 20. But what are you really doing when you're plugging in 4, when you're plugging in -4? What you're really doing is you're using a bunch of limit laws. For example, this is the limit of a quotient. So we're allowed to use that 5th limit law. And say, look, the limit of x squared plus 14x over x plus 2 is the limit of x squared plus 14x over the limit of x plus 2. And we can go a little further and say, hey, look, we can split that limit up over addition in the numerator and the denominator, right? So this plus this limit over this plus this limit. And we can do it even a little bit more, right? We can say, well, x squared is really x times x, and 14x is really 14 times x, so we can use properties 4 and 3 to say this. Right, because it's the limit of x times the limit of x. And we can pull that 14 right out. Oh, that's -4, I guess. And then I guess we're going to keep the bottom the same, so much so that I'm actually just going to, copy and paste this. Right there. Perfect. And now, at this point, it's basic enough to say, look, the limit as x approaches -4 of x is just -4, right? Now it makes sense to plug in -4 when we can. And of course, in the case of 2, it's just 2, right? And now if you simplify it out, you get 20. So just to let you know that when we do this, we're really doing all of this, just for you to know. Now, why are limit laws important? Well, because they tell us what we can and can't do. If we look at example 3, for example, right, we have this limit. Limit as t approaches 0 of 1 over t root 1 plus t minus 1 over t. Now, you might look at this and try to plug in t equals 0 and say, oh, okay, well, I guess we have infinity, 1 over 0, that's, infinity minus infinity. You might be inclined to think that that's 0. But it's not. We don't get to use the subtraction limit law because infinity does not exist. So we have to get this in the form of something that does exist, where we can use limit laws. So what we're going to do here is we're going to simplify the fraction by finding a common denominator. Right? So when we simplify that, we're going to get 1 minus root 1 plus t all over t root 1 plus t. From there, if we try to plug in t equals 0, we get 0 over 0. Well, maybe I'll do it over here. You'll see why in a sec. We get 0 over 0. Another indeterminate form, annoying. Yes, both of these right here are indeterminate form. Right? This is. But at least this one is something we're more familiar with. And if you remember from last time, we know how to handle this, right? Multiply by, the conjugate over the conjugate. Right? Now, the bottom is going to be messy as always, but the top is going to simplify pretty nicely. It's going to be 1 minus 1 plus t. Right, now remember that minus sign, right? More on that in a sec. Now, just be a little careful here when we simplify. This is a mistake that's very common and very easy to make, but it can be very damaging. Note that 1 minus the quantity 1 plus t equals 1 minus 1 minus t, right? That minus sign distributes over the parentheses, okay? So when we simplify this, right, usually after multiplying by the conjugate, we're able to simplify immediately. Be very careful that your fraction has a negative t in the top. All right, and so then, of course, we can divide out. But keep in mind that we still have a negative 1 in the numerator. All right, and at this point, we can plug in t equals 0, and we wind up getting negative 1 over 2. I'll let you simplify that. So just to point out, why did I say using limit laws? We didn't need to do all of this limit separation, blah, 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 blah. But the point was that we needed to do all of these extra steps because infinity minus infinity was not something we could work with. Now let's go to section 2.6, where limit laws also are very relevant, right? One nice thing about limit laws is they also work when x approaches just gets arbitrarily higher or smaller, right? It approaches infinity or negative infinity, right? Without bound. Now, infinity and negative infinity are not numbers. So we can't treat them like numbers. So we have to be a little careful when we get infinite answers. That said, we can still use limit laws. So let's take a look at this. So we have something like this. What happens if we plug in negative infinity? Well, we get negative infinity over negative infinity. This is not helpful because we can't use limit laws. So we need to have limits that exist in the numerator and the denominator. So the way to do that is, well, the leading terms are the things that are giving us problems, right? They're the things that blow up the biggest compared to the other. Yeah, like this 6x squared and this minus 4x, they also go to infinity, but they're just completely dwarfed by these leading terms. So we're going to look at the leading terms, and we're just going to divide by the one with the lower power, but it turns out they're the same power in this case, right? They're both x cubed. So when you do that, look what happens. 4x cubed becomes 4. 6x squared becomes 6 over x, and negative 2 becomes negative 2 over x cubed. And in the denominator, we have something similar. Now, I don't like repeated fractions any more than the next guy, but they do help us out in this case, because we now have limits in the numerator and denominator that exist. So now we get to use our limit laws and say that our limits are, now let's take a second here. When we sort of plug in infinity, by which I mean we plug in a million, a billion, a trillion, we see what happens as x increases without bound. What happens to this number, or this number, or this, or this? Well, the top is fixed, and the bottom increases without bound, so we get 0. So we just get 2. We had to do this important, crucial step in order to get our answer, because we needed to use limit laws. Even if you can kind of see, oh, look, these increase at roughly the same rate, it's going to be 4 over 2, it's going to be 2. That's not enough for a mastery, because you need to illustrate why the limit is 4 over 2. You need to use limit laws. Now let's take a look at example 5, a little more challenging. Right? X, once again, approaching infinity. I guess not negative infinity, but positive infinity. Here we have something, well, again, we have this sort of infinity minus infinity situation, right? Where this gets big, right? And so what happens there? Well, it's another indeterminate form, and maybe we remember from last time what we do. Right, we have a radical, an indeterminate form, we're adding or we're subtracting something, so let's multiply by the conjugate. All right. Multiply by the conjugate. Now, I don't love turning a non-fraction into a fraction, but it's kind of the only thing we can do in this case. Right? Make sure to square that 3x when you subtract it. And the bottom, not going to be as messy as before, but it is, you know, a bottom. It is denominator, which we didn't have before. Notice that we can cancel out the 9x squareds. That's very nice. And notice that if we plug in infinity again, so to speak, we're going to get infinity over infinity. Another indeterminate form, but something we're a little more familiar with now. So now what we're going to do is we're going to multiply the top and the bottom by 1 over x, right? Knock off that leading term. Now you might be saying, oh, isn't the leading term in the bottom x squared? No, it's the square root of x squared. It's x, right? So this will give us the limit as x approaches infinity of 1 over, now let's be a little careful here. I hope we see that the plus 3x is going to turn into a plus 3 when we divide by x. But what's going to happen over here? Well, we're going to have the square root of 9x squared plus x divided by x, which I guess is the same thing as divided by the square root of x squared, which I guess is the same thing as the square root of all of that over x squared, right? You can just combine the the radicals like that. With multiplication division, you can combine the radicals. Let's make this a little neater, right? We have that, okay? That, okay? All right, now at this point, just a little bit of arithmetic, right? We're not using any crazy machinery here, just a lot of arithmetic, right? So we have 9x squared over x squared plus x over x squared plus 3, right? So I hope you see that these will cancel. That'll cancel like that, and we have a 1 over x, right? Right, so we're left with a limit as x approaches infinity, 1 over the square root of 9, whoops, sorry, I guess it's 9 plus 1 over x, and then separately plus 3, and then that winds up giving us 1/6. Okay? So a little bit of an extra step, right? Multiply by the conjugate first, then divide by the leading term, and then plug in. Slight shift of gears here. We're going to define a number that is basically, it's defined using a limit at infinity. So I guess now is a good time as any to define it. The number is called E. Yes, the number is E. I said that correctly. It stands for Euler, the guy who did a lot of work with it. If you're interested in where it comes from, probably the most relevant real-world example is continuously compounded interest. Anyway, it's the limit as x approaches infinity of 1 plus 1 over x to the x. And you might think that that's just 1. You might think it's infinite. It turns out it's approximately 2.72. Now, why is this number important? Well, it's not clear yet. But it is important, and it'll be very apparent later on when we learn about things called derivatives. So just sort of keep it in the back of your mind. But let's just do a little bit of work with E. Just treat it like a number. Just treat it like the number 3 for right now. So if we want to find the limit as x approaches infinity of e to the negative x, well, just like anything else, we know that negative exponents means 1 over the positive exponent, right? 1 over your number to the positive exponent. Top is fixed, bottom blows up. The answer is 0. Let's be a little more careful with example 7, right? Because x is approaching negative infinity. Weird things can happen with negative exponents, right, as we saw. Right, well, this is going to be a large negative number, and we just showed that that's going to give us 0. So that's our answer. Let's go on to example 9 really quickly. Even though we're dealing with an exponential function, not a polynomial, right, because the x is in the exponent, not in the base, we can use similar techniques, right? If we try to evaluate this limit straight up, we get infinity, or I guess it's negative infinity over infinity. So I guess what we can do is maybe with a similar trick as before, do that. And now we're going to get this. This will be 1 over e to the x minus 1 over 1 over e to the x plus 2. And if you want, you could note that this is the same as e to the negative x minus 1 over e to the negative x plus 2, just because we showed that that equaled 0. Anyway, this equals 0 minus 1 over 0 plus 2, which is negative 1/2. Okay. Now, slight digression, but one last limit at infinity. Remember the graph of sine of x, right? It oscillates over time. It never really settles on any one value. So if we're just talking about x increasing without bound, well, this is sort of unusual because the limit isn't infinity or negative infinity or a number or whatever. It just does not exist. Okay? More on that next time when we learn the squeeze theorem.